from a particular value of x, where the value of the function is known, the farther away from it in general, the less of a good job the straight line approximation does in actually approximating it. But we'll begin with example 3. Use differentials in the graph of f to approximate the following. And it's on the top of the next page if you have your notes. F of 2.06 and f of 1.9. Now from the graph, we have the function, and we also have the point on the graph, 2, 7. We probably should confirm, just so it doesn't end up pulling your leg or something like that, that f of 2 actually does equal 7. So let's just confirm that. F of 2 equals 2 cubed minus 6 times 2 plus 11. That's 8 minus 12 plus 11. That's negative 4 plus 11, and that's 7. So f of 2 does equal 7, and the point 27 is on the graph. So what we'd want to do is use this information to evaluate the function, or approximate the value of the function, at a couple of numbers that are close to 2. The value of the function is known at 2, since we just punched it in there. We got 7. What if we want to find the value of the function at a number close to 2? Well, one option, of course, is to take the 2.06 and plug it in. 2.06 cubed minus 6 times 2.06 plus 11. That will give us the exact answer, and maybe that's not all that difficult to do. But here is, well, here are a couple of alternatives to that. If we take this equation, y equals x cubed minus 6x plus 11, and write it in, take the derivative and write it in differential notation, dy dx equals 3x squared minus 6, easy enough to find the derivative. And we're treating dx like an independent variable, so we multiply both sides by dx and write dy equals 3x squared minus 6 times dx. So dy is not exactly the difference between the known function value and the function value that we want. That's delta y. Delta y is f of, let me write it somewhere, delta y in our case, delta y is going to be f of 2.06 minus f of 2. We know f of 2 is 7, and so f of 2.06 maybe is close to 7. If we look at the picture, it looks like it's a little greater than 7 because the function's increasing right there. That's our delta y. If we knew the difference between f of 2, which is 7, and f of 2.06, which is a little bit more than 7, we could just add it, and we would have the value. But we don't know how much the function is going to increase between 2 and 2.06. So we consider the slope. The slope of the tangent line, the slope of the curve at 2. Let's see, what would that be? 3 times 2 squared, 3 times 4 is 12, and 12 minus 6 is 6. So m sub tan equals 6. The slope of the tangent line is 6. So we don't know exactly how much the function increases between 2 and 2.06, but the straight line, if it has a slope of 6, if we go 0.06 units to the right, we'll go 6 times that many units up. Does that make sense? 0.06 if the slope is 6. If we go 0.06 to the right, we'll go 6 times that many, 0.36, I believe is what that is, 0.36 units up. So I have to zoom in on this to see what's going on, but 0.06 to the right, 0.36 units up, so it would seem like we could take f of 2, which is 7, add 6 times 0.06, we would get 7 plus 0.36, and that's 7.36. And this would serve as an approximation to the value of the function. And the closer it is, in theory, the better an approximation it is, the closer it is to the actual value. So what is the actual value? If we were to take 2.06 and cube it, and then subtract 6 times 2.06, and then add 11, we get 7.38 something. And you know the point, because it's concave up throughout that interval, we would expect it to be a little bit above where the straight line is. The straight line is below the graph there. So 7.36 seems like a reasonable approximation. If we were just looking at this, to find dy, scoot this out of the way, to find dy, it's going to be 3 times 2 squared minus 6 times the value of dx, but dx equals delta x, and that equals 0.06. For our purposes, dx and delta x are always going to be the same. Dx and delta x always the same. Dy, we hope, is going to be close to delta y, and thus can be used as an approximation for delta y. But dx, delta x are going to be the same. Dx equals delta x equals 0.06, so 0.06. Dy equals 6 times 0.06, which is 0.36. And so the actual delta y, this would be like 7.38 something. What is it? 7.38, 1816, and who knows if that's rounded, minus 7. Delta y equals 0.38, 1816, or somewhere thereabouts. Dy is 0.36, and it's kind of close. Kind of close. So we're using this as an approximation for the delta y. Let's try it with the f of 1.9. And here's my thinking with this one. I kind of looked at this one two different ways. So let's try it just the one way, just with the dy. Just with the dy for the f of 1.9 to see what we get. So I need to copy a little bit of this and then scoot to the next page. F of 1.9, we're wondering what's that approximately equal to. Well, in this case, delta x is actually negative 0.1. It differs, this is how it differs from the known value of 2. We know the value of the function f at 2, and it's 0.1 less than 2, so the delta x is negative 0.1. So that's also going to be our dx. dx equals delta x equals negative 0.1. Dy is going to be 3 times negative 0.1 squared minus 6 times dx, which is negative 0.1. So if we're on the graph and the slope of the tangent line is 6 and we go 0.1 units to the left, we would expect to go 0.6 units down. Is that how it would work? This is, oh wow, what is that? 3 times 0.01 minus 6 times negative 0.1 dy equals 0.03 minus 6 times what am I doing there? What am I doing? That's x. It's not delta x. It's x. I'm so sorry. It's still 2. And we've already done this calculation. So I'm wasting your time. Sorry about that. The slope is 6. Slope is still 6. But this time we go we go 0.1 units to the left, so we go 0.6 units down. dy equals negative 0.6. There we go. So 0.6 of a unit down. So from the y value of 7, this is we can say delta y is approximately equal to this. So we can say f of 1.9 is approximately equal to f of 2 plus the delta y. Actually, it's exactly equal to f of 2 plus delta y. It's approximately equal f of 2 plus dy. That's 7 plus negative 0.6, which is 6.4. 6.4. Is that close to the actual value? Maybe. 1.9 cubed minus 6 times 1.9 plus 11. Kind of. Again, let's see, the curve, the actual curve is above the tangent line, so we would expect that value also to be greater than our approximation. Okay. Hopefully to something that seems a little bit more meaningful, since we have a square root button on our 99-cent Walmart calculator, and this one is not that difficult to evaluate a polynomial function, so it seems kind of senseless to try to approximate something that can be evaluated exactly so easily. Error propagation. The idea here is we're going to measure something, and then we're going to do a calculation, basically evaluate a function at a number derived from a measurement that's made. Now, if there's some intrinsic error, we measure something and we get an answer, plus or minus whatever the degree of precision our measuring device is, then that when we use that measured value to evaluate a function or some formula, do a calculation, our answer, that error will propagate itself into the answer. So there'll be some error that's intrinsic to our answer, and basically the idea is we want to know how much. If we know the error in the measurement that we made is no more than this much, then we'd like to be able to say the error that's involved in our final answer after doing this calculation based on the measured value maybe is no more than this much. And if we can say that, if it's okay that we're off by no more than that much, then we're good. But we want to be able to quantify or to express the error or the possible error in our final answer in terms of the error that's known in the measurement that we make. That's the idea. So we use the idea of differentials to do this when we study error propagation. So let's copy this little bit for the discussion, and I'm going to attempt a similar picture to one that I drew last time. We're going to let x denote the measured value of x, and we're going to use x in a calculation. So let's see, there's some function, and we measure, and we come up with a value of x, and that is the measured value of x. It may not be the exact value of x. We may be off by as much as delta x. Okay, so worst case scenario, the true value of x is delta x units away from this. So the true value of x is x plus delta x. Now delta x itself could be positive or it could be negative. I've got to draw the picture one way or the other, so I'm going to draw the picture so delta x looks like it's positive. So I'm going to say delta x is over here. It looks like a horrible measurement. We're way off. Nope, sorry. Delta x is the difference between them. Delta x is the distance from there to there, and this is x plus delta x. We're off by at most delta x. That's the degree of error in our measurement, or the actual amount of error in our measurement. So we want to do a comparison here to to f of x. We're going to take this x, and we've got a formula that we've all worked out, and we're going to evaluate this formula using the x, and we're going to get an answer, and the answer that we get is going to be f of y. Sorry, f of x. It's going to be f of x. But the actual value is f of x plus delta x. If we take the true value, that we don't know and never will know, but the true value, if we were to evaluate the function there, what we would get is f of x plus delta x. Now, if we consider this difference here, let's see, there to there, that's going to be, let's see, oh no, let's try this there. That's going to be f of x plus delta x minus f of x. And this is called the propagated error, and we'll denote it by delta y. There's at most delta x amount of error in our measurement. Our measured value is f of x. We evaluate the function, and we get f of x, and we're wondering how far is that off from the actual value? Well, at most delta y, which would be f of x plus delta x minus f of x. Now, generally, it may be difficult to calculate the value of f of x plus delta x minus f of x. So what we want to do is approximate that using dy. So we have our function, y equals f of x, that's our function, and we take the derivative at x, and we come up with the slope of the tangent line, f prime of x. There's the tangent line. M sub tan equals f prime of x. Or dy dx. So this is delta x in between there, but we could also regard it as dx. Dx and delta x throughout this section are going to be exactly the same. There's a dx, there's a delta x, they're exactly the same. dy is going to be used as an approximation for delta y. We want to know we can be off by this much. Well, dx is going to be kind of close to that. So what's the difference between dx and, dy is going to be close to that. What's the difference between dy and delta y? Well, dy, think of the idea of slope. dy over dx, rise over run, is the slope of that tangent line. So from here to here, that's dy. Compare that to delta y. Now, the way I've drawn the picture, there is somewhat of a discrepancy between dy and delta y, the little amount in red there. But if delta x is a little bit smaller, then maybe it's not such a bad approximation for the propagated error. So basically, the dy is going to be used as an estimate for the error that takes place, or the possible error that exists in our calculation, if dx is the possible error that exists in our measurement. So we want to find dy and use that as an approximation for delta y. That's the idea in these calculations. Here goes. It's another ladder leaning against a wall. "12-foot ladder this time. Leaning against a wall makes an angle theta with the floor." Let's see what this would look like. There's the floor. There's the wall. There's the ladder. There's theta. There's 12 feet. If the top of the ladder is y feet up the wall, express y in terms of theta. Trigonometry problem, we can do that. And then approximate the error in estimating y if theta equals 60 degrees plus or minus a half a degree. Error in estimating y if theta equals 60 degrees plus or minus a degree. Let's see, okay. So let's express y in terms of theta. Y is the length of the opposite side. 12 is the hypotenuse. So it looks like a job for sine theta. Sine theta equals side opposite divided by hypotenuse. So y equals 12 feet times sine theta. So if you give me the value of theta, I can punch it in there, take the sine of theta, multiply by 12, and if we know it's an exact value of theta, I can give basically, and I guess we also kind of have to know we're assuming this. We're assuming there's no error in the 12. Whoever measured the 12, the length of the ladder, got it perfect. That's an assumption here. In real life, maybe not. But we're assuming that so we don't have error from that measurement as well. So we know the 12 exactly, and we know the theta exactly. Then 12 times the sine of that exact value of theta would be the exact height of the ladder up against the wall. Top of the ladder from above the floor. But if we could be off a little bit in the measurement of the angle theta by as much as half a degree, then maybe we'd be off by a little bit too much if the angle, if we think the angle is what, more than it really is. Or maybe we'll say it's too little if we think the angle is less than what it really is, too low. So let's see here. Let's calculate dy and use that as an estimation of delta y, how far off we may be with these values. So dy dx equals 12 feet times the dx, really? Dy d theta equals 12 feet times the cosine of theta. So dy equals 12 feet times the cosine of theta d theta.
Why did that change to the cosine?
Oh, it took the derivative.
Oh,
Yeah.
well, then why doesn't 12 become 0?
Because it's a constant multiple rule. I think, yeah, constant multiple rule, is that the one? Derivative of a constant times the function is a constant times the derivative of the function.
Oh.
Yeah. So we use the value of 60 degrees for theta. Now the thing with d theta though, for theta, and I've mentioned this before and I'll keep mentioning it because it really does cause a lot of confusion. It doesn't matter whether we take the cosine of 60 degrees or the cosine of pi over 3, did I get that right? Radians. so long as our calculator is in the correct mode. Right? Cosine of 60 degrees or the cosine of pi over 3 radians. Doesn't matter. We get 1/2, right? I think. But it matters what we put in for d theta, because that needs to be a pure angle measure. That can't be degrees, that has to be radians. So if I may be off by as much as half a degree, I've got to convert that to radians. It just doesn't make sense to substitute 0.5 degrees for d theta. When we substitute an actual number for x or for theta in one of these, it's got to be a pure angle. So 0.5 degrees, if I want to know how many radians that is, I would need to multiply by pi over 180. Pi radians over 180 degrees. So that's going to be, well, let's just do this. .008726. Put too many zeros, didn't I? No, I didn't. .008726. Ultimately, we won't need that many decimal places, but they're not going to hurt. So dy equals 12 feet times the cosine of 60 degrees times 0.008726. And I think we can get that by taking the 0.008726, multiplying it by 6, or multiplying it by 12, and by the, I just don't know what mode my calculator's in. Now I do. It's in degree mode. Multiply by the cosine of 60 degrees. And I get 0.052 feet. Which is how many inches? A little more than a half an inch, 0.6 inches. So we measured the angle, and we got 60 degrees for the measurement of the angle, but we know the way we measure angles, we might be off by as much as half a degree one way or the other. What we're saying is, based on our estimate of dy for delta y, we're going to be off by no more than about 0.052 feet or 0.63 inches in our calculation of how high the top of the ladder is above the floor. That's what we're saying. Just for fun, of course, what we should do is actually do the calculation. We should say, suppose it's actually 60.5 degrees. So y is 12 times the sine of 65 degrees. Nope, 60.5 degrees. And 12, did we actually do this calculation? 12 times the sine of 60 degrees? I don't know if we did that calculation. How far apart are those? Or maybe it was actually this, 59.5 degrees. See, if we say it's 10.39, maybe it's as much as 10.44, maybe it's as little as 10.34, but our estimate is we can be off by about 0.05 feet. See, we're looking at the delta y here. The difference between those is delta y. Difference between those is delta y, and we're using dy as an approximation for that. It looks like a pretty decent approximation in this case. All right, the area of the circle is to be computed. Sorry, a word there. Area of a circle is to be computed from a measured value of its circumference. I'm trying to think why we would want to do such a thing. Maybe it's a tree. I want to calculate the cross-sectional area of a portion of a tree without drilling straight through the tree to measure the diameter or to try to measure the radius. We measure the circumference of the tree, and then based on that we should be able to calculate the area. It would help if we had a formula for the area of the circle in terms of its circumference. It's not too tough to come by, I think, because we can express the radius in terms of the circumference, right? Circumference equals 2 pi r. So r equals c over 2 pi. Area equals pi r squared. So area equals pi times c over 2 pi, quantity squared. So area equals pi times c squared over 4 pi squared. So area equals c squared over 4 pi.
Are we going to come up with that?
What?
Are we going to have to come up with that?
Oh, you can handle that. That's no problem. Just algebra. Just algebra. No trouble there. Or you can just memorize it, an alternate formula for the area of a circle. Next time someone asks you for the area of a circle, you say c squared over 4 pi. That'll freak them out. Big time. It'll freak me out. You told me that. But it expresses the area in terms of the circumference rather than the radius, as we're all accustomed to, pi r squared. Yeah. So use differentials to estimate the error in the calculated area if the circumference is measured to be 48.7 centimeters, and we know we could be off by as much as 0.2 of a centimeter in our measurement. Let's see. So this is our A. A equals, let's say, 1 over 4 pi times c squared. So what we want to do, the error in the area is delta A. We want to approximate that using dA. So we want to find dA. dA, so we're thinking take the derivative, maybe dA dc. That's going to be what, 1 over 2 pi times c. Take the 2, multiply by the 1 over 4 pi, and the 2 divides in the 4 2 times, and you get 1 over 2 pi. So dA dc equals, oh no, I just said that. TA equals 1 over 2 pi times c times c dc. C equals 48.7 centimeters. That's the measured value of the circumference. DC is 0.2 centimeters. C equals 48.7 centimeters. DC equals delta C equals 0.2 centimeters. So we're going to substitute those quantities into the right-hand side. And see what the possible error in the calculation of the area is. dA equals 1 over 2 pi times 48.7 centimeters times 0.2 centimeters. Well, it will be square centimeters. Let's see what. 1 divided by, careful with this one, if you would like to have the 2 pi as a factor of the denominator, maybe put it in parentheses. 1 over 2 pi times 48.7 times 0.2, 1.55 square centimeters. square centimeters. So we measure the area based on this circumference. Now, if you're more comfortable with the pi r squared, we can do that. But we'd have to calculate the radius of this circle. So circumference, let the calculator go away for a moment. Circumference equals 2 pi r. So r does equal c over 2 pi. So if we take the c, 48.7, and divide by 2 and divide by pi, the radius of the circle is about 7.75. So let's calculate the area of the circle based on this. So pi times, I think significant figures I'll be okay. 7.75 squared. So the area of the circle, based on our calculation, would be about 188. I'm worried. Let's keep that number in mind, but let's just compare it. I feel like I should use the circumference to calculate the area since we worked so hard on that formula. What was it? 1 over 4 pi c squared? It was 1 divided by 4 pi times c squared, so times 48.7 to the second power. Is this going to compare favorably with what we have? I think they should only agree to 3 significant figures. Yeah, they agree with the 188. I like this better. 188.73. So we're looking at this, but we may be off by as much as 1.55 square centimeters. So what if we use 48.5 centimeters? What if our measurement is 0.2 of a centimeter too much? It was actually 48.5. So 1 divided by 4 pi times 48.5 square centimeters. The difference between that and the calculated value above it, is that around in the neighborhood of 1.55? Does it look like it? Looks like it. And what if we were to low, and it's actually as much as 48.9 centimeters for the circumference. If we compare that to the top value on the screen, is that in the neighborhood of 1.55 square centimeters greater than that? Yeah. So it looks like if it's actually 48.5 or it's actually 48.9, we're going to be off by no more than about 1.55 square centimeters. So this is an estimate of how far off the calculated value of the area is going to be based on how far off our measured value is. What is the percentage error in the measurement of the circumference? Is this just horrible that we're measuring the circumference of this cross-sectional area, this tree cross-section, and we might be off by as much as 1.55 square centimeters? Is that horrible? Or is that pretty good?
That's what you're doing with it.
Well, I guess it could depend on what we're doing with it. If this is off by as much as what, 50%, if the actual value is 3 square centimeters, we could be off, and we're off by as much as 1.55 square centimeters, that's pretty bad. But if the actual value is 3,000 or 30,000 square centimeters, and we're off by 1.55, that might be a really, really good measurement. So what's the percentage error? Well, we take the estimated error, dA, and divide by the calculated value, A, and multiply by 100%. estimated error divided by calculated value multiplied by 100%. So it's going to be 1.55 square centimeters. Wait, I'm answering the next question. So sorry. So sorry. What's the percentage error in the calculation of the area? That's what I'm doing there. And I calculated the area to be 188.73 square centimeters. We'll do that in a moment. What is the percentage error in the measurement of the circumference? That's going to be our DC divided by C times 100%. DC and delta C equal to each other. So DC over C, that's going to be 0.2 centimeters divided by 48.7 centimeters times 100%. Let's see what that one is. 0.2 divided by 48.7. So this is going to be 0.4%, or 0.41%. Seems like it's pretty good. It depends on, I guess, what it's going to be used for. But less than 0.5% error there. I think a good question would be, if our estimate of the circumference is off by only 0.41% of the actual circumference, does that mean that our estimate, that our calculated value of the area is going to be off by no more than 0.41% of the actual area? Well, maybe. And maybe not. The area is 0.82. 0.82%. So if our measured value of the circumference is off by as much as 0.41% of the actual circumference, then the calculated value of the area may be off by as much as 0.82% of the actual value of the area, calculated value of the area.
Exactly twice that.
It is exactly twice that, and I believe we can show that. I think we can express dA over A in terms of DC over C without having to use too much trickery. Let's see. How could we do this? dA over A we could express C, so dA over dC. Let the wheels turn on that one a little bit. I've done that before, but not on limited sleep. So let me save my energy maybe. Yeah, it can be shown. It's exactly twice. It is not just coincidence. It is exactly twice. Calculating differentials. If we consider these rules and compare them to rules that we have for derivatives. We have a constant multiple rule for derivatives. If we have the derivative of a constant times a function, then that's equal to the constant times the derivative of a function. If we're dealing with differentials, then the differential of a constant times a variable is equal to that constant times the differential of that variable. The differential of the sum of two variables is going to be the sum, or difference, I guess I should say, of the differentials. There's something akin to the product rule that works for differentials. And there's also something akin to the quotient rule that works for differentials. One example kind of to showcase for this where I believe that this product rule for differentials comes into play. But we'll refer back to this rule when we get there. And we're there. Example 6. The circumference of a right circular cylinder is measured to be 95.7 centimeters with a possible error of 0.05 centimeters. The height of the cylinder is measured to be 275 centimeters with a possible error of plus or minus 0.5 centimeters. Find the volume and use differentials to approximate the propagated error in computing the volume of the cylinder. If we want to go further and calculate the relative error, the percent error, if we convert it to a percent, we can, but let's just see if we can find the approximate propagated error. What is the formula for this? Well, let's see. What is the formula for the volume of a right circular cylinder? In terms of, ooh, that's a rough looking radius there. Radius and the height. In terms of the radius and the height, the volume is the area of the base times the height. So pi r squared times h. What we know is that C is 95.7 centimeters and DC is 0.05 centimeters. We are also given that H is 275 centimeters and DH is 0.5 centimeters. Given information. We want to find dV, okay, the possible error in our calculation of the volume if we use these values. So we need an expression for dV, and that's going to mean taking this and calculating the differentials. Well, here goes. dV equals, and let's see how this, basically it's the differential of a product there applies something akin to the product rule. So see if this makes sense. The differential of pi r squared h. So dV, first let's do the constant multiple rule. Take the pi out in front. So the pi can come out in front, basically like that. So this is going to be pi times, or pi times the differential of r squared h. Now, what looks like the product rule, dV equals pi times the first times the differential of the second plus the second times the differential of the first now we're good except, see, we can substitute wow. We don't know R, do we? I'm going to finish this because this is useful. but we don't know r. Suppose we did know r, this is how it would go. dv equals pi times r squared dh plus, this is going to look like the chain rule, h times 2 dr. What if it were the derivative of r times r? And we use the product rule for that. It would be r, the first times the differential of the second, plus the second times the differential of the first, it would be 2r dr. So I've left out an r. All right, it would seem that we just take the 2 out in front and then have 2 dr. But the problem is, what if we were taking the derivative of r squared? Wouldn't that be 2r times the derivative of r? So this should be 2r times the differential of r. So we need an r there, like that. It's a shame we can't use that. But there it is. What do we have to do since we know the circumference? Instead of pi r squared, it's...
Can't we find r using circumference?
We can. We can find r, but then I have to convert this 0.05 because that's the possible error in the measure of the circumference. And I would have to convert that to the possible error in the radius. Now we could just plug that into the formula as well. But I don't know, either way it sounds difficult to me.
The circumference is pi r squared. So
Well, 2 pi r, so we would just have to basically c equals 2 pi r, so we could take all the values and say c over 2 pi, and say if we have 0.05 possible error in the measure of circumference, then whatever that is would be the possible error in the measure of the radius. I think it would work, but let me go ahead and do this one and see how much worse it is. dv pi r squared is c over 4 pi, 1 over 4 pi c squared h. No, that's v. So now we need dv. dv, let's not take the extra step with the constant. Or maybe we will. 1 over 4 pi times c squared d, c squared h.
I'm lost.
What?
Where did C come from?
Oh, it was from up here. I think it's right. Was it this one? Oh, I erased it. I have to derive that again. I erased it. It was if area equals pi r squared, area could also be expressed as 1 over 4 pi times c squared. That's where that was from. So I just picked up the pi r squared, since that's the area of the circular base, and I replaced that with 1 over 4 pi c squared. So, I mean, it may be serendipitous. It might be helpful to compare these two. these two differential formulas and see if we see anything in common, make a connection there. So dV equals 1 over 4 pi d c squared h. So using the constant multiple rule, the differential of a constant times an expression is that constant times the differential of the expression. dV equals 1 over 4 pi. And now something akin to the product rule. I don't know how much more this is going to tell us. Basically what we did before. It's the first times the differential of the second plus the second times the differential of the first. We have to be really careful with the differential of c squared. dV equals 1 over 4 pi. So that's c squared dh plus h times, yeah, CDC.
2CDC, isn't it?
It is 2CDC, thank you. So the derivative of c squared is going to be 2c times, I keep saying derivative, the differential of c squared is going to be 2c times the differential of c. So 2c dc. There we go. So all that really changed was the constant. Instead of pi, it's 1 over 4 pi. Now we evaluate dV equals 1 over 4 pi times, let's see, 95.7 centimeters squared times dH. dH is 0.5 centimeters plus h. H is 275 centimeters times 2 times c, that's 95.7 centimeters, times dc, that's 0.05 centimeters. dV equals, well, calculator time, I think. 1 divided by quantity 4 pi times, ooh, this looks dangerous, 95.7 squared times 0.5 plus 275 times 2 times 95.7 times 0.05. Will that do it? $573 maybe call it 574 cubic centimeters. So I wonder if this is a relatively small portion if we compare it to the calculated volume. If we compare this to V, which would be, we use the right formula, 1 over 4 pi times 95.7 centimeters squared times 275 centimeters. If we did that calculation, would 574 centimeters be a very small percentage of that volume? Is this a big error? I can be off by as much as 574 square centimeters, or it's a really big cylinder and maybe I'm not off by all that much, comparatively speaking. What do you think? 1 divided by 4 pi times 95.7 squared times, whoops, Come on. Times 275. So the calculated volume is 200,000 cubic centimeters. And the calculated volume is 200,000 cubic centimeters, and we're estimating that we're going to be off by no more than 574 cubic centimeters. What, I need to divide and then take the reciprocal? Then, yeah, off by around no more than 0.3%. Maybe that's not that bad.
Unless you're dealing with explosive chemicals.
Oh, then it may be bad. Depends on the situation. All right. Let's see. Let's say a little bit about 5.1.
And find the value.
What?
Yeah, that question there. It says and use differentials. I think it
And
was supposed to be and then use differentials.
and then use differentials, yes,
Yeah.
to approximate the propagated error in the computed volume. I'll fix it someday, maybe. 5.1. Antiderivatives and indefinite integration. Yes, starting a new chapter, the final few minutes of class. But I think it's kind of interesting to think backwards. Feel good about thinking forwards, right? We've been finding derivatives for quite some time. So we spend a little bit of time thinking backwards. All right. So definition. Function f is called an antiderivative of a function on an interval I if you take the derivative of big F, that antiderivative, and it equals f of x for all x in the interval. So an antiderivative is a function whose derivative equals the function that it's an antiderivative of for all values of x in that interval. So can you think of one antiderivative of 3x squared? Some function you can take the derivative of and get 3x squared. X cubed. X cubed, that works. So big F, I'll say big F sub 1 of x equals x cubed. This works. Big F sub 1 prime of x is sure enough 3x squared. What's another function you might take the derivative of and get 3x squared?
X cubed plus anything, like a constant.
X cubed plus anything like a constant. So f sub 2 of x equals
Cube plus k or something.
like, yeah, x cubed plus k or something. There. A constant, I guess, something, you know, not x, not k plus, you know. X cubed plus k, pick a constant. So x cubed plus 5, x cubed plus 13, x cubed minus pi. Any function that differs from x cubed by a constant is going to be an antiderivative for this function. So that said find 3. This is basically all of them if you let k be any real number. So so this is plenty of antiderivatives for 3x squared. Now, hopefully it's believable.
So basically, this is antiderivative is basically reverse engineering the original function.
Basically so. We're thinking backwards. We're thinking, what do we start with to get that as the derivative? And up to a constant, this next theorem tells us that if we can find any antiderivative, then all other antiderivatives must be of the form big F of x plus a constant. So if we find big F, and that's any antiderivative of f on the interval I, then for any constant, g of x is big F of x plus c is also an antiderivative. That's easy enough to check. Just take the derivative, and g prime of x equals f prime of x. But what's a little bit stronger, we won't prove it, but it's a stronger statement, is that every antiderivative, if there's an antiderivative at all, it must differ from that first antiderivative that we found by some constant. The process of finding derivatives was called differentiation. The process of finding antiderivatives could be called anti-differentiation. We will more commonly call it integration. Integration is going to be how we'll denote it. So if we could take the derivative of big F of x and get little f of x, all antiderivatives of little f of x are of the form big F of x plus a constant. So that's the way we'll write it. So the notation for it, the notation involves a symbol which is intended to resemble an elongated letter S standing for the idea of a sum. We'll talk about sums later in the chapter and see how sums, infinite sums, can be converted to integrals. But we write this and we say the integral of f of x dx equals big F of x plus c. So big F is an antiderivative of little f. We can also call this, when we use this notation with the integral sign, that expression is the integral of little f of x dx. So we got the example here. The integral of 4x cubed dx, we know if we take the derivative of x to the fourth, we get 4x cubed. So x to the fourth is one function that would be an antiderivative of 4x cubed. So you could say the integral of 4x cubed dx equals x to the fourth plus any constant. This is the notation that we'll use. The dx notation tells us the variable with respect to we're integrating. In Calc 3 especially, when you do multiple integrals, there could be various different variables in the integrand. And you need to know, am I integrating with respect to x? Am I integrating with respect to y? In most cases, we'll be integrating with respect to x in this class, but the dx will tell us that we're integrating with respect to x. More notation. The symbol is the integral sign. F of x, the function whose antiderivative we're searching for, is called the integrand. X is the variable of integration. And let's see. Oh, c is called the constant of integration. So basically, we'll take the integrand and we'll search for any antiderivative at all, any function whose derivative is equal to f of x. Once we have that, we can just say plus c, and that will represent the set of all antiderivatives of that expression, little f of x. Some more examples. Example 2, write an equivalent integration formula for each derivative formula given below. We know that d dx of 4x equals 4. So that means the integral of 4 dx. So we try to think, what can we take the derivative of and get 4? Well, 4x plus 5, 4x minus 11, or just plain old 4x. Keep it simple. Take the derivative of 4x, that would give us 4. So the expression 4x plus c represents the set of all antiderivatives of the constant function 4. Dx there. Sorry, d dx of 1/5 x to the 5th equals x to the 4th. So we're wondering if we write it using integration notation, the integral of x to the 4th dx. We search high, we search low. What could we possibly take the derivative of to get x to the 4th as the answer? Well, would this make sense? This is going to be called the power rule for integration. Let's see if this makes sense. If we're taking a derivative, we take the exponent out in front, multiply by the exponent, and reduce the exponent by 1. What if we reverse those in the reverse order? Invert them in the reverse order. What's the opposite of reducing the exponent by 1? Adding 1 to the exponent. And then what's the opposite of multiplying by the exponent? Dividing by the exponent. So how about if we add 1 to the exponent and then divide by the exponent. That will give us an expression that whose derivative is x to the fourth. So the integral of 4x to the negative 1/3 dx. If we add 1 to the exponent, what is negative 1/3 plus 3/3?
1/3.
Did I say it right? Negative 1/3 plus 3/3 is going to get us all the way up to 2/3. And then if we divide by 2/3, that's equivalent to multiplying by 3/2. But I've also got a 4 to contend with, don't I?
So it's like multiplying by 6.
Like that, plus c. So this equals 6x to the 2/3 plus c. We know the derivative of sine x is cosine x. So we've got cosine x, so we're wondering, what can we take the derivative of to get cosine x? Oh, sine x, that's it. So sine x plus c is the set of all antiderivatives for cosine x. And I hope we're starting to feel good about derivatives of e to the power of some function of x, e to the 3x in this case. If we take the derivative of e to the 3x, we get 3e to the 3x. So if we're looking for an antiderivative of 3e to the 3x dx, officially we'll use a process called integration by substitution to do this sort of thing. But it's e to the 3x plus c. E to the 3x is one function you can take the derivative of and get 3e to the 3x. Every other function that you can take the derivative of and get 3e to the 3x is of this form, e to the 3x plus c.